At the end of the previous lecture, I mentioned that the perturbation series of quantum electrodynamics is only an asymptotic series, and in particular it has 0 radius of convergence, because the theory is unstable for any value of the fine structure constant less than 0. So, let me give an argument to support this statement, which was formulated by Dyson. So, the argument considers the theory with alpha less than 0 and that corresponds to a situation where like charges attract and unlike charges repel. To see this, one just has to note the Coulomb force between two charges, and it is proportional to alpha. So, if you flip the sign of alpha, the behavior of Coulomb force between two charges basically reverses from what is it is in the real world. And this situation where like charges attract and unlike charges repel is unstable for any value of alpha less than 0, and the argument essentially parallels what we know about the theory of gravity, where the force is against 1 over r squared structure, and like charges, which are the masses in the theory of gravity, they attract. So, this situation in particular in gravity we do not have unlike charges, there are only like charges and they attract, and then there is a unstable situation of a collapse of the system to an energy which is unbounded from below. The attraction collapses and this does not occur automatically in the quantum system, because even though the potential can be attractive, there is a limitation coming essentially from the uncertainty relation, where you cannot localize the objects to arbitrary precision without enhancing its kinetic energy, and one has to balance the potential and kinetic energy. We have seen this situation in the case of hydrogen atom. The potential is unbounded from below, 1 over r goes to infinity when r goes to 0, but the hydrogen atom is stable, the electron does not fall and sit in the center on top of the proton, as would be expected from the classical theory. In quantum theory, the electron remains around the orbit, and so the situation does not arise just by saying that the potential is unbounded from below, but there is a balance which has to be achieved between the quantum uncertainty, which gives rise to a finite size of the system, and the potential which tries to collapse the system towards a point. Now, what happens in case of gravity is that if the number of particles involved are not very large, then a star does burn out its fuel and it collapses to a situation which is known as white dwarf, but that white dwarf remains gravitationally stable and nothing further happens to it. If one increases the number of particles, the white dwarf can change to a neutron star, but there comes a limit where if the number of particles which are mutually attracting becomes large enough, the star will become a black hole, and that is actually a singular situation corresponding to an unbounded from below total energy, and that is the collapse which indicates that the whole theory has become unstable and there must be something else if we want to survive the theory, and the real solution in case of gravity is not known. It probably would involve a quantum theory of gravity, but for our purpose it is sufficient that when there are mutually attracting particles and a sufficiently large number of them, they can collapse even in a quantum theory to a singular unbounded from below in energy state, and that is what we would like to avoid in case of electrodynamics with alpha less than 0. Now, and these mutually attracting particles, I should say, can lead to this situation because the force involved is long range. It is a 1 over r potential which does not allow any screening, and it can act at very large distances. So, with 1 over r potential and no screening, massive star can collapse to a black hole. And let us see this argument little more explicitly, that in case of electrodynamics, what we expect from quantum fluctuations produce pairs of E plus and E minus, which tunnel to a state where all electrons say collect in one region and all positrons collect in another region far away, and this is a state of what can be called spontaneous polarization with energy of the order of sum over I, where I is the particle number mc square plus kinetic energy. This is for each group, and since there are two groups, I will put factor of 2 and plus the interaction energy, which is summed over all possible pairs. Prime just means that the situation with I equal to j is not counted, and I will assume that each group has n particles and the two groups are quite far away from each other. So, can ignore the interaction between the group, which is tiny. So, now we can see the magnitude of each of these three effects. So, let us say that there are n pairs produced which spontaneously polarize in this way. The first term is order n. The last term, if we take the groups to be far away, can be made negligible, but the interaction within the group is of order alpha n square, and that is the crucial point, that the interaction energy grows as quadratic function of the number of pairs, while kinetic energy and the rest mass energy only grow linearly. And so, this can be negative for sufficiently large n for alpha less than 0. And that is the crucial point, that one may require a large enough number of particles to collapse the state, but since the function is n square for the attraction energy, no matter how small but negative alpha there may be, one can always find a large enough value of n when this happens. So, for those many numbers of pairs produced from the vacuum, the theory will suddenly spontaneously polarize and collapse to a state with energy unbounded from below. And this is a signal that there is instability, that instability occurs in spite of the quantum uncertainty principle, just as in the case of a black hole. And so, we have a theory which is singular and we have a branch cut along the negative axis in the complex alpha plane. So, that was a statement which I made at the beginning, and this is a argument which supports the statement. So, now we can ask, well, the theory is such that the perturbation expansion is not going to be a convergent series, but can it still be useful? And the answer is that the expansion is useful in the sense of an asymptotic series. And here one has to recall what is the property or characteristic behavior of an asymptotic series. The asymptotic series diverges for fixed alpha and number of terms going to infinity, but at a fixed order, that means you do not sum all the terms all the way to arbitrary large power, but decide on a particular order. So, that I will consider only say 10 terms in the series. Then it provides a answer which approaches the correct value, and here we have to assume that there must be some other formulation of the theory which gives a correct valid answer. That may not be a series expansion, but some other kind of a calculation, and this happens to a better and better accuracy as alpha becomes smaller and smaller. So, if alpha is small enough, one can rely on this second property that one does not have to consider a very high order series, just consider a finite truncation of it, and that answer may be accurate enough and it converges towards the correct value as alpha is taken closer to 0. So, typically the successive terms of such a series first decrease in value and then so, for a few terms, if you look, the successive terms are becoming smaller, it seems to be approaching some value, and then suddenly you find that the terms start becoming larger and larger, many times oscillating in sign, and the point of adding more and more terms to the series does not make sense, because the new corrections which are coming in are much larger than the value which you would expect to be meaningful. So, this is a behavior, and the point that is important is to figure out how many numbers of this asymptotic series make sense. One has to find an exact solution of very simple cases where the same criteria apply and one can compare the asymptotic expansion versus the exact solution and see how well it works. In our particular question of electrodynamics, this situation is a two body problem, the same hydrogen atom situation where we could solve and get an exact answer, and alpha greater than 0, the hydrogen atom solution gives such a where one can again ask about when situations become unstable, and in this particular case there is no spontaneous polarization as happened in case of alpha less than 0, but there is still the instability in the two body problem that one can have one E plus and one E minus mutually attracting, and when they can collapse or when they can provide a potential energy that can overcome the kinetic barrier. So, the energy of a positronium is order minus alpha square m c square. We have calculated this, and which indicates instability for alpha greater than approximately 1, and this is indeed true if there were charges involved which are not the charges of the electron, then the alpha will be replaced by Z1 Z2 times alpha in this analysis, and one has the answer that Z1 Z2 times alpha should not exceed 1 for the theory to be stable. So, this is a criterion which we just derived by looking at alpha as a general parameter. Of course, in the real world alpha is about 1 over 137, and this instability which corresponds to again a spontaneous pair production out of the vacuum, but for a single pair. So, this is instability for a single pair production, different from the instability for a large number of pair production which we dealt with in the case for alpha less than 0. So, this is a behavior, and in real world the series of this particular type can be obtained by looking at the order by order behavior and see which where this whole analysis goes, and we want an asymptotic series of this particular one can work little backwards and figure out that an asymptotic series whose terms are behaving as n factorial times alpha to the n, it will never converge for any value of alpha, no matter how small, but its successive terms will fall and they will start diverging only when the number n crosses 1 over alpha. And so, in case of QED, the expectation is that the series will be meaningful up to order 137. We are nowhere in our calculational capability to reach anywhere near the order. The base calculations are of fifth or sixth order in alpha, something of that type. And so, the series actually is very well behaved, and one can see that the successive terms are decreasing in the real calculations with alpha equal to and things work very well, but there is a similar theory which is applicable to strong interaction. It is also a gauge theory, but with a different structure, and in particular its coupling constant alpha is order 1. In this particular case, easily observed in that particular case that the series terms do appear for a first few terms to be becoming smaller, but then they suddenly start increasing, and there is no point in trying to calculate to higher order and sum various things up. So, this is a important digression in understanding the meaning of this perturbative series before trying to attempt a calculation and trying to compare it to experiments. Now, let me add one more point in this analysis or description of nature of perturbation series, and which has to do with the properties of the S matrix. So, generally momentum conservation constraints keep the intermediate states in the Feynman diagram, which we have been describing as propagators of shell, and we will see this occurring explicitly in many examples to be worked out. But there can occur situations, but when this can change when new states, the states which are not described as asymptotic states, appear in the theory, and we see the signatures of various kind of situations which may occur in the explicit answer for the S matrix. I will mention two instances, that a single propagator becoming on shell represents a bound state in the theory, and in terms of S matrix, the propagator was just a simple polynomial in the denominator. So, it shows up as a pole in the S matrix. The S matrix was just a product of all the propagator terms and vertices which do not have any problems as far as singularity are concerned. One can have more than one propagator also becoming on shell, and that will represent many separate bound states appearing in the theory, or when the share a common vertex represent what can be called production thresholds. Instead of a bound state, and in terms of the S matrix, this will be represented by branch cuts. So, both these situations occur, and every time they show up, yes, we have a new dynamical feature of the theory to understand, and one has two ways to go about looking at this situation. Of course, one straightforward way is to just expand the theory to include all these new states and their decay properties as well as production property in the analysis, and then you will have a much larger theory where these problems will go away. Or one can stick to the same theory, but try to express the singularities in terms of behavior and constraints about where the theory is well behaved and above which particular points one has to look for new effects, and that is done. So, new effects can be assigned to such singularities of the S matrix and which generically lead to expansion of the theory. And the tool which is most useful in this particular analysis, the treatment of all these poles and branch cuts is easily done. So, these features are properly handled by extending the S matrix into planes where all the momenta become complex, and then one can ask the same situations, and when the meaning of this poles and branch cut becomes much more appropriate in the sense of dealing with functions of complex numbers. And in particular, one can note that there are poles and singularities appeared because the denominator could become 0 with these factors of p square minus m square cancelling out because there are signs coming from the Minkowski metric, and there are no singularities for what are known as Euclidean momenta, where instead of the Minkowski metric we have just the Euclidean metric delta mu nu, and then all the 4 components of p square add, and they are all positive numbers, and that mathematical expression can never be 0 and one has no singularity. So, one can connect these two features from Minkowski space to Euclidean space by doing an analytic continuation in the complex momenta plane, and then one can describe the behavior of what is happening around the poles and the branch cuts much more accurately. And this technique of analytical continuation it provides many constraints on the properties of the S matrix, and these properties many times are beyond the restriction of perturbative expansions. They are far more general, and they are in that particular sense powerful constraint on the whole structure of quantum field theory. So, I will not go too much into details of the analysis of this analytical continuation, but it is a useful feature to know that such things can be done. We might use a few instances of this Euclidean connection to do very simple calculations, and that will come in the later part of the course. So, with all this background, we have built up the background to do explicit calculations and understand the physical consequences, and that is what I would now turn to. And let me just introduce the topic of various kind of processes. And then calculate from the scattering amplitude what is the rates of this process here, which are often describes in terms of cross sections. And I will stick to tree level processes because these are much easier to handle than the one which involves loop, but maybe I will make a comments about various loops at a later stage. So, let me give some examples. The simplest example is that of Coulomb scattering. There is a heavy nucleus producing certain electric field, and the projectile basically scatters off from that field, while the heavy nucleus hardly moves, or rather it recoils, but it recoils very little, and in the Coulomb scattering that recoil is ignored. So, in terms of Feynman diagram, the process can be described as some projectile coming in I, some projectile going out F after hitting the electromagnetic field, and that interaction is represented by this photon, and that photon is produced by some nucleus, which I am denoting by a cross here, and this photon is not a real propagating photon, but it is a photon representing a Coulomb field, which is a virtual photon denoted by gamma with a star on it. So, this is a virtual photon from a static nucleus provides the field. So, this is a process, and we can calculate its amplitude and corresponding scattering, and we will do that later. Let me first only give a related processes. The second common process which I would like to mention is Compton scattering, where there is not a virtual photon, but there is a real photon which actually hits a electron and is absorbed and re-emitted. So, one can denote it by this particular diagram, but now there is a alternative available in a different ordering of the processes in the quantum world, because everything intermediate is summed over the whole space time, and all particular time orderings can occur. So, the alternative is that first final photon is emitted, and then the initial photon is absorbed, and this again we will see how to calculate it, but now one has to add the two diagrams, and the relative sign between these two processes depends on the ordering of the two photons, and it just happens to be positive, because photons are bosons and interchanging them does not give any extra sign which we have to track of. But in real world, the Compton scattering is not done on a free electron, but it is a process. So, which can be described as E minus gamma going to E minus gamma, and the electron is often bound in atoms. Even though it may be bound in atoms, or it could be there in metals, the scattering can occur, and then one can again calculate the rates of these particular processes. In the same symbolic language, the Coulomb scattering would be a process where E minus gamma star will lead to E minus. Let me mention another common process. It has the name Bremse-Strahlung. which means literally breaking radiation, and what happens is the electron in this particular case emits a photon and slows down. And so, it is kind of reverse of this Coulomb scattering, but again it cannot emit a real photon like this because of energy momentum conservation. Something else must be there to absorb the recoil, and in this can occur in external electric field. And again this in real world is just initial or final state radiation. And in terms of diagrams, though the reaction shows only one photon, the external electric field does appear as a virtual photon in the process, and so the diagram will appear that the photon is in a final state, but an virtual gamma star from the external electric field like in the Coulomb potential is absorbed, and again in the same way there are two possible ordering where the photon can be emitted before or after the virtual photon from the electric field is absorbed. And so, there are two diagrams. Again the ordering between the two bosons does not give any signs, and the two contributions have to be added. Again more correctly I should put a gamma star for the external field in this particular process. So, these are the simple processes involving radiation. I would give some more examples of simple processes next time before going on to details of calculations one by one.